Hi, everyone. Thank you so much for the invitation to the Lathisms organizers. My name is Nicole Gonzalez. I am currently a postdoc. Tell you about today is a bit of what I do, in particular, a story about that starts in combinatorics, ends in knot theory, and then comes back again to combinatorics. So the main goal here is to show you how we can use combinatorial structures and, in particular, symmetric functions to develop some theorems and some new information about questions in knot theory. So let me start. So the first object I want to talk about are some very old numbers. They're known as Catalan numbers. And they're really some of the most, as it says here, ubiquitous sequences of integers in combinatorics, but also in representation theory, algebraic geometry, and many other fields. So here we see some of them, right? So this is the nth Catalan number. It's 1 over n plus 1 times 2n choose n. And here we see the first few terms written out. And yeah, if these are really numbers that show up everywhere, in particular, some of the things that I care about that they count are things like the number of non-crossing partitions of integers 1 through n. They also count the number of ordered trees on n plus 1 vertices, but many and many other things. So if at some point, during this talk, you want to pause and you wonder how this connects to you, what your area is, I highly encourage you to do that. I guarantee you Catalan numbers will probably count something you are interested in. For the purposes of this talk, the things that we are most interested in that they count are dig paths. So Catalan numbers count the number of dig paths in an n by n square. Let me tell you what that means. So for us, a dig path is just going to be a lattice path that you can draw consisting of only vertical or horizontal steps that are bounded by a diagonal, in this case of, let's say, slope 1, right, with endpoints being 3 and 3. So this would be the dig paths of corresponding to n equals 3. And as we see, we draw the diagonal, right, in all of these cases, and we're looking for paths that start and end at each of these points, but that never go past the diagonal. So they're bounded above by the diagonal. And again, they consist of vertical or horizontal steps exclusively. So here we see some of them, right? So the first one, which is in some sense kind of the biggest staircase or the biggest lattice path you can hope for, which is as close to the diagonal as possible. But you have many others. You could have, for example, this one that we've highlighted here. You have this one. You can have this one. And there's actually one that I'm missing, which is the one where you do nothing. So you can imagine that you just went like this, and I forgot to draw it. So there are actually 5 total dig paths in this particular example. And indeed, we see that for n equals 3, the third Catalan number is 5, which is exactly corresponding to the 5 dig paths when the endpoints are 3 and 3. Now, a different way of thinking about a dig path is in terms of what we call in combinatorics partitions. So a partition is nothing more than just a sequence of numbers, let's say lambda 1 through lambda k, with the condition that the numbers are weakly decreasing. So, and positive, right? So here, how do we, dig out the partitions from each of these examples? Well, they're pretty easy to read. So here we have 2 and 1, and then 0, we just read the rows bounded by the path itself. So this would be the partition 2, 1, 0. In this case, we have 1, 0, 0, right? 1, 0, 0. We have 1, 1, 0. And then we have 2, 0, 0. And so you see that when we do this, and indeed I highlighted the non-zero parts in green in these pictures, you end up with a weakly decreasing sequence of numbers that are non-negative. So we can think of a path as either just a lattice path or equivalently as the sequence of numbers, and we will be using this duality as we go through. Okay, so what we're actually going to be interested in today is a generalization of these Catalan numbers. So there are many ways of generalizing Catalan numbers. One particular method is using a polynomial modification or a polynomial generalization. We're going to call these the Qt Catalan polynomials, and they're polynomials in two variables, q and t, that generalize these Catalan numbers by essentially adding two gradings or two ways of getting the value, the exponent of the q and an exponent of a t, so a qt monomial, out of every single path. The way we do this is as follows. So formally, the formula for these Qt Catalan polynomials is what we see here, right? So it's going to be a polynomial in variables q and t. We have q to some exponent, t to some exponent. I'll talk about that in a second. And each of these exponents are indexed by one dig path, each of the dig paths, so it's indexed by each of the dig paths that are bounded underneath this line, as we said, with slope 1 and let me draw this a little bit better. Let's say slope 1, but endpoints n and n. So that's what this n here would correspond to. So for each such path, we can somehow get this value of area and dinv out of it. The way we do this is as follows. So the area, so the exponent of the q, is just the number of complete boxes between the path and the diagonal line. So let me go back a slide. And so, for example, here, the area is 0 because there are no complete boxes between the path and the diagonal. Here, we have one complete box and another complete box. And so that tells me that the area in this second picture is 2. The area here, we only have one complete box. And so we have 1. And here again, the area is 1 because we only have one complete box. So anytime you have a box that's slashed, that's not entirely contained within the path, right, and the diagonal, you don't count it. So that's what the area is going to count. It's kind of like the complement of the partition that we were just labeling. All right, so that's the area. That gives you the q, the exponent of the q variable. The dinv is a bit more complicated. And what it morally counts, and I'll do this slightly in an example here, it's the number of horizontal steps that lie above and on the same diagonal of a given vertical step. So just bear with me here. So for example, here we have n equals 2. These are the only two paths that you can draw whose endpoints are 2 and 2, right? And so the area, like I said, is pretty easy. Here, the area is this box, area of 1. The area is 0 because there are no complete boxes bounded between the path and the diagonal line. Dinv is morally the way you count it, and this is not exactly correct, is you want to imagine that you're going to take this line and you're going to slide it. And for every vertical step, you're going to look at the horizontal steps above it. So here, as I slide it, as I slide it, I look at, I look at this horizontal step first, this vertical step, and I look to the right. I look to the left. I look to the left because it's above and on the same diagonal. So above it, so to the left, there are no more horizontal steps, so it doesn't contribute anything. Likewise, if I were to slide this up without messing up my path, my next vertical step is this one, but once again, above it, there are no horizontal steps, so I get a dinv of 0. On the other hand, if I were to play a similar game here, in this other, I have 2 vertical steps, and if I slide this and I count, let's say at first I do the bottom vertical step, and I look to its right, then you'll notice that I have one horizontal step to the right one horizontal step to the right of this vertical step that I've circled, that is intersected by the same diagonal. I have to keep the slope fixed as I slide it down, right? And if you can imagine that if there were some other horizontal step here secretly, then the contribution wouldn't be 1, but it would be 2, because you would get this intersection and you would get an intersection with this. And you do this for every single vertical step. You look to the right and you look at how many horizontal steps are being intersected by that line of the same slope. You add all these values and you end up with some number. And that number is essentially what dinv is. So here, let me erase all my little contributions here. So that's why here you end up with a div of 1. That's essentially how this works. And so when you do this, this allows you to compute essentially the coefficients, or the exponent, sorry, of q and t. All right, and you end up with a monomial, q to some power, t to some power, for every single path that you draw. So for example, when n equals 2, the second qt Catalan polynomial is, well, for this first picture, you get a q to the 1, a t to the 0. And for the second picture, you get a q to the 0, a t to the 1. So it's q plus t. And the claim is that these polynomials generalize the qt Catalan numbers. And indeed, they do when you plug in the variables q and t equal to 1. And let's check that. So here, if I plug in q and t equal to 1, I end up with 1 plus 1. This is 2, which if we go back to the previous page, you'll notice that that is exactly the second Catalan number. So that's, in that sense, that's how they generalize it. Another observation that won't play such a key role in this talk, but isn't very important, is that this polynomial, if you'll notice, is symmetric under exchanging the q and the t. So it's qt symmetric. And this is always going to be true. This procedure, it's not obvious at all, is going to give you a polynomial that is always symmetric under swapping the q's and the t's. Very well. So are these the only sort of polynomials that we're going to consider? No. It turns out there are many generalizations of it. In particular, there's no reason that our line that is bounding our paths, we have some sort of family of paths bounded by this diagonal. There's no reason this diagonal has to have slope 1, right? There's no reason that the intercepts have to be the same number. And indeed, we have the so-called rational Catalan polynomials, where you allow the intercepts to be integers, any integers, as long as so that the slope is some rational number. And generally, you take the GCD to be 1, but that's for computational reasons. And so when you do this, you end up with the so-called rational Catalan polynomials. Of course, you might ask, well, what's special about rational numbers? Actually, nothing. And so, sure, let's let the numbers be real instead of just rational. And then these are called the real or triangular. This word will come up later. But for all intents and purposes, let's just call them the real Catalan polynomials. And again, they're going to be always indexed by the endpoints of our line, right? The slope of our line, essentially. And then there's another generalization, which is commonly studied, which is basically you bound also by a diagonal line, but now you ask, well, what if I allow my lattice paths to not only consist of horizontal and vertical steps, but also of diagonal steps, right? So you allow some fixed number of diagonal steps in this path, always bounded above by some line of some slope. That's always fixed. And indeed, when you do this, you end up with another family, which we're going to call the QT Schroeder polynomials. And these are indexed by two numbers, n being, in this case, 3 and 3. So here we are fixing the slope to be 1. We won't need to, and that's in fact a generalization that we consider later on. But for all intents and purposes, right now for these diagonal lines, we are only allowing the slope to be 1, so the intercepts have to be the same. And then D is going to tell you how many diagonal steps you're allowed to take. So in these two examples, D is equal to 1 because we have exactly one step that was allowed to be diagonal. And obviously, if you let D equal 0, then you have no diagonal steps, in which case you are just back in the land of the classical QT Catalan polynomials that we studied at the very beginning. So these are all various generalizations of these polynomials that we had before. So you might ask, what do these count, right? All of these polynomials, by virtue of generalizing each other, generalize as well the QT Catalan numbers. So of course, why are they even interesting? What are they counting? Well, it turns out that these QT Catalan polynomials, all the generalizations I just mentioned, and these associated Schroeder polynomials, show up also in various places in representation theory, geometry, combinatorics, and knot theory. I will try to tell you about 2 of them today, depending on the time, but I will probably only be able to tell you about 1. We'll see. So let's focus on the knot theory connection, and maybe we'll get to the representation theory. So let's see. So to tell you about the knot theory connection, I need to give you a little bit of background on knot theory. So let's put the combinatorics on hold for a second. We will come back to it. So fundamental question in low-dimensional topology is, if I give you two knots, how do you tell them apart? And what do I mean by a knot? I mean exactly what you are imagining. I take a piece of string, I tie it around, and then I glue the ends together. So something like, oh, I glue it around. I maybe say something like this. See if I can draw it better. Something like this. I tie it around, whatever, and then I glue the endpoints back together. And then when I do this, I end up with, in this case, maybe this was a trivial knot, but you can make it so that the knot is not, it doesn't just undo itself. And this is it. But of course, I could have taken this and imagine if it's a three-dimensional object, I could have wiggled it a little bit differently. And then when I try to draw it, and I draw the projection on this piece of paper, it's going to look differently. And so the whole point is, you can't tell knots apart because you could wiggle them and they visually could look very differently, but just looking at them. So mathematicians, to try to make this much more precise, developed an algebraic way of telling knots apart via what are called polynomial invariants. What these do is essentially, you want to think of them as a machine that eats a knot, and for every knot, it spits out a polynomial. There are many of these. I'll discuss a few of them in a second. But when I say it's an invariant, any sort of knot invariant, right? This is encoding the fact that if I give you two knots that are isotopic, which is to say two knots that if you give you knot one, I can wiggle it without breaking the string, just by wiggling it like in 3 dimensions, I can get to the other knot. So if there is a sequence of wiggle moves or isotopies that take me from one knot to the other, then I want my machine to spit out the same polynomial necessarily, because the knots are topologically the same. However, if the knots are different, which is to say there is no sequence, there's no way that I can take this knot and wiggle it to become some other knot, just somehow that there is no method by which these two things can be made, or the sequence of steps can be made, then I want my machine to spit out different polynomials, right? So you want to think about this machine, this polynomial invariant, as a sieve, essentially. It distinguishes the knots if they're different, or if the knots are the same, then it tells you these knots look different, but they're secretly the same because the polynomial is exactly the same. So there are many examples of such polynomial invariants. Some of the most well-studied are, for example, the Jones polynomial, the Alexander polynomial, or the Homfley-Petit polynomial, which I will compute very shortly, which generalizes both of these polynomials into one. It's a polynomial in two variables. What's the upshot of these kind of classical polynomial invariants? Well, that they're actually pretty easy to compute, at least on an example basis, right? So if I give you a knot and I say, here's a very specific knot, here's the picture of it, compute it by hand or with a computer, you can do it fairly easily. It's not necessarily the most effective computation, but you can do it, and we'll do it on the next page. The problem, right, the issue is that these machines that we have, these polynomial invariants, don't distinguish every knot. They're not perfect sieves. So there are many examples where there are two knots that we know are different for other reasons, but if you feed them through any of these machines, the polynomial that they spit out are the same. So the machine is telling us the knots are the same, but we know for other reasons that these knots are actually different. So that's a problem, because that means this machine distinguishes some knots, but it's not perfect, right? It's not a perfect sieve. It's not doing its job exactly as we want it to do. So there's a solution to this, or a partial solution, which we will get to. But before I do that, let me give you the idea of how these knot invariants are computed, these polynomial invariants. So we're going to do the Homfley-Petit example. This is this Homfley-Petit polynomial, which is going to be a polynomial in two variables, a and q. So step one is you want to take a planar presentation of the knot. That just means take your favorite knot and project it onto a piece of paper. Just draw it so that you keep track of whether you have an over or an under crossing. And then you have to fix two values. So the first value is you want to fix the value of the unknot. The unknot is literally just the knot with no knots in it, like a rubber band. And this is just a normalization. I'm choosing it to be 1. You can normalize it to be many, many different things. And then the second relation is what's known as the skein relation. And what this does is this allows you to relate a crossing that looks like this to a crossing that looks like this. As you see, these two crossings are essentially the same, except the strings, the order in which the strings are presented is swapped. That makes a huge difference because this relation is what's going to allow us to untangle the knot, as we will see. And then we resolve locally, which means you just recursively apply these relations until you end up with a polynomial. So how do you do it? So let's suppose my example is this guy here, right? And I'm scaling it by a so that the equation is easier to apply and I don't have denominators, but the a just comes along for the ride, basically. So here I have, two strings, they're knotted together. And what I want to do is I want to focus on one of these two crossings. I'm choosing the top crossing, but I could have just as well chosen the bottom one. It doesn't matter. Once I've chosen the top crossing, I want to notice that locally, and this is this whole point, locally, this section looks exactly like this section, right? And so what I want to do is I want to apply this linear combination locally in this picture while leaving everything outside of that blue circle intact. So this crossing, which is this guy here, can be written as a linear combination of this guy and this guy. So that's exactly what I do, right? I replace this picture with this picture, and then this picture becomes this picture. Notice everything outside of the circle is completely untouched. And now I want to notice that when I do this, now this has, the consequence of this computation or this procedure is that now the top string is completely disjoint from the one on the bottom, right? I can just separate them because they're not linked, they're not knotted anymore, right? Because you really have to imagine that these are legitimate three-dimensional objects that you can move around in space, right? And when I do this, then this becomes essentially two separate disjoint rubber bands, two different circles. And then this one, well, I can just rotate it, right? Because again, you're allowed to wiggle things. Wiggling is always allowed. And so, great. So if I do that, then this just becomes, again, my rubber band. And so what I've achieved is I've written this knot here as a linear combination of rubber bands, essentially. When I do this, because I've know what the value of my rubber band is, right? Each of these guys is precisely a copy of the unknot. They all evaluate to 1 according to my normalization, and I end up with some expression. In this particular, it's not exactly a polynomial because I chose my normalization to be 1. So if you choose your normalization to be something slightly different, you can normalize denominators essentially, and you end up with a polynomial. So that's why these are called, this is why it's normally called the Homfley-Petit polynomial. But either way, the point is this is generally pretty easy to compute by hand. But like I said, it's not great because it doesn't work to distinguish every knot. So how do we fix it? Well, the modern approach to this is by appealing to homological invariants. A homological invariant is the following. So it's a machine that eats a knot, but now instead of spitting out a polynomial, it spits out a chain complex, which is a much more complicated algebraic object. So for those of you who don't remember what a chain complex is, imagine that you take a family of vector spaces, let's say V1, V2, V3. Maybe it's an infinite family, maybe it's a finite family, Vn plus 1, maybe there are more. And then I have a series of maps that connect them. We're going to call these maps differentials. So I have a family of maps. Let's call this D1, D2, D3, Dn, etc. That satisfy a very specific relation, which is that when you compute them one after the other, you get 0. So in this particular case, you want dn plus 1 followed by dn to equal 0 for all n, right? So d2 composed with d1 has to be 0, d3 after d2 has to be 0. So normally this is you just say d squared equals 0 because you think of this as kind of a giant family of maps. So that's a chain complex. Of course, you can make these objects be something more interesting than vector spaces, and normally you do. But morally, this is it. It's just a sequence of spaces, for example, vector spaces with some maps that square to 0. So in this particular example, or this particular construction, the chain complex can be many different things, depending on which, what they call homology theory you're computing. The particular homology theory that we will be interested in today is a homology theory known as Combinatorics homology. And what it does is it assigns to a knot a chain complex, but consisting of triply graded vector spaces. So again, you have these vector spaces, you have these maps between them, but each of the vector spaces admits 3 different gradients. So when you do this, so there's 3 gradings in the chain complex. When you do this, something you can always do with a chain complex and with a vector space in general is you can take its graded dimension. So this is a dimension where for every different for every dimension of the vector space, you end up with an exponent. So this allows you to compute what is known as the Poincare polynomial of this associated chain complex. So what I mean by this is, let's say you have a vector space and it has 3 gradings. So let's say it's Vijk. Ijk denote the 3 distinct gradings associated to your vector space. Then to this, you can assign something of the form q to the I, t to the j, let's say a to the k. So each of the gradings become the exponents of your variables. That's really all that's happening here. And so because you have a family of vector spaces, this becomes basically a sum of things of the form something like this. And this gives you a polynomial. It's morally what you're doing here. Great. So this allows you to compute a triply graded polynomial, which is known as the Poincare polynomial of the associated chain complex, and therefore of the associated knot that you started with. So the upshot of this construction is that this homology theory, this much more complicated construction, is actually better not invariant, right? So in particular, one of the issues that we had with the Hompley-PT polynomial and all these polynomial invariants is that there are many cases where the knots are different, but the polynomial that you get is the same. Here, this Combinatorics homology, it still has that same issue. There are still cases where the knots are the same, but the output is, sorry, the knots are different, but the output is the same. But despite that problem, it still tells more knots apart. So it does everything that the previous, it tells everything apart that the previous polynomial invariants did, but there are more knots that it distinguishes, if that makes sense. It's a finer sieve. It's not a perfect sieve, but it's a finer sieve. So that's why we say it's a strictly stronger invariant. And in particular, it does what's known as, it categorifies the Hompley-PT polynomial. So categorification is a totally different topic I don't want to necessarily delve into today, but in this context, it just means that if you take the graded Euler characteristic of this chain complex, you actually recover this Hompley-PT polynomial, which was that polynomial we just computed in 2 variables in that example. So basically, you get all the old information, but you get some new information because the object itself, this chain complex, is more interesting. It's more complicated and has more information. And that can just be seen by the fact that you end up with a polynomial with 3 variables versus 2 variables. And that extra variable has more info. That's it. So that's the upshot. What's the problem? Well, as you can imagine, the issue with this is that it's a hard homology theory to compute. Just from the definition, right? It's quite difficult. And because it's difficult to compute, it's really only known explicitly for very small families of knots, in particular, the MN torus knots, which I'll describe in a second. So that formulates the following issue, which is, well, how do we compute it for more families of examples? So let me talk about these MN torus knots and tell you how this relates back to the combinatorics. So an MN torus knot is the following construction. I'll do it through an example because that in general it's exactly the same and you'll get the gist. So let's suppose you have m equals 3 and n equals 4. you want to start with, let's say, 4 strands here. Do it with the highlighter. So sorry, this is being weird. Great. So there we go. So we start with 4 strands. And then the idea is that the 3 is going to tell us how many times we're going to wrap around from behind. So we take the bottom strand and we basically wrap it through the back. That's 1. And then we do it again. The bottom strand up through behind. And that's 2. And then we take the bottom strand up through the behind, and that's 3. So that's the 3 kind of wraparounds. And then once you've done this procedure, you just take these 3 strands, or sorry, these 4 strands, you take these 4 strands, and then you just glue them together without knotting them anymore. So I don't want these to overlap in any way. I just want them to be completely non-interacting. So unknotted. And they just glue themselves back together. And so when you do this, let me erase all my ugly annotations here. When you do this, there's another way of thinking about these knots, and that's why they're called torus knots, is because you can think of this picture as being drawn on top of a little square, right? And this is exactly the same thing. So these strands here are exactly these guys here that I've drawn in black. And and then the connections in the back, these guys are just these dotted strings in the back. So the way that you get a knot is by remembering that you can identify a square with a torus or a donut by first you identify the top and the bottom edges and you glue that together, right? You end up with a cylinder. And then in the next step, if you identify the edges, you glue a cylinder along the edges, you get a donut. And so if you do that with this picture, so you glue this guy with this guy, that's how you end up with the back strands identified. And if you glue this side with this side, the end result is that these strands will be identified. You end up with this, and you end up with this, which is exactly the same picture as I drew here. It's just a different way of drawing it. So that's why they're called torus knots. Now, how is this relevant to the story at all? Well, and this is where the combinatorics comes in. One of the things that was proven by Hogenkamp and Mellett is they gave us a way of computing the homology, this Kowanek-Brzezinski homology, for this family of Mn torus knots, where M and N are any relatively prime integers. And they proved that when this is true, when you have this knot, this polynomial, this Poincare polynomial that we just talked about in the previous slide, actually coincide with these Mn rational Qt Catalan numbers. So this is this rational Qt Catalan polynomial. Right? And notice that here, the a is 0. So I got rid of one of the variables. So it specializes to the rational Qt Catalan polynomial. Which is amazing. Like, why would something having to do with dig paths and lattice paths have anything to do with knot theory? So that begs the question, like I said, first of all right, can we compute these polynomials for larger families of knots? So knots other than this particular family of Mn torus knots. There are many knots in the world. So can we actually compute it? And secondly, if we were to compute it, do we end up with another relation analogous to this one right here between that computation and these other Qt Catalan polynomials that we talked about, right? Because these were these rational guys where the slope is rational, but you could imagine that the slope could be real. You could imagine that you allow diagonal lines and you talk about Schroeder polynomials. So there are many other generalizations of Catalan polynomials. Are those related to knots at all? So that's what we're going to try to answer today. And the answer is yes. So to do this, I need to introduce yet another family of knots, a much more general one called Coxeter knots. So again, our goal here is to introduce a new family of knots and then essentially generalize this theorem. Right? Connect this new family of knots to combinatorics. So to do this, let's define them. So a little bit of history. These Coxeter knots, or more generally Coxeter links, were originally studied by Alexei Oblomkov and Lev Brzezinski geometrically, and then more recently in the last few years were studied by Pavel Galashin and Thomas Lamb combinatorially under the name of monotone links, but these are completely the same object, just have different names. And the way that you construct them is the following. So you start, the input is a partition. So remember that a partition is a decreasing sequence of numbers that are non-negative, right? So some tau 1 greater than tau 2, tau k greater than or equal to 0. So some decreasing sequence of numbers. And then associated to this decreasing sequence of numbers, I want to choose, this is a choice, a curve, a monotone decreasing curve, so that this partition that I've selected is the maximal partition beneath it. Let's do an example. So here, let's say my partition in this example is 2, 1, 1, 0. So tau is 2, 1, 1, 0. All right, so 2, 1, 2, 1, 1, 0. And I want to pick C, this curve, to be just any curve as long as it bounds essentially your partition. So I could have chosen my partition, my curve to be something like this. As long as it's monotone decreasing, I don't care. I could have chosen it to be, I couldn't have chosen it to be a straight line, actually, in this particular case, because notice if I do this, then my partition would be bigger. I could choose my partition to be something larger. And that's exactly what I want to avoid. So basically, you just choose any partition so that the number of lattice points underneath it is exactly the same lattice points that the partition cuts out, if that makes it easier to understand. Okay, so you've chosen your partition, and the way that you get a knot out of this picture is the following procedure. So you're going to start with the top right corner here. Top left corner here. And you're going to read down the path. And for every single square, you're going to project it onto this square on the right. So we start with the first one. You see the highlighted bit, that becomes that. Then I read the next part, and that becomes this. I continue reading down my diagram. This guy becomes this strand here, and so on. Right, the next bit gets projected onto the line. And something to point out, so as you're drawing this, depending on the slope of your line, the lines might overlap when you overlay them on top of the same square. That's okay. And notice that here I made a choice to kind of say that this new strand is underneath all the previous ones. And that's just a choice. So as long as you consistently make a choice that the newer strands get added underneath the older ones, or conversely, that all the new strands get added on top of all the old ones, as long as that choice is consistent, it doesn't matter which choice you make. So here I'm just choosing every new one gets added underneath. Every new one gets added underneath. And that's why I have this sort of picture here. All right, so I continue with my picture. Next one gets, added here. Next one, and notice that I'm literally just projecting this little square onto here. That's all I'm doing. I'm just projecting each little lattice. And then I do the next part, and finally the next piece. And so this turns this curve that I've selected into a picture on a square, where now I have some overlapping strings on top of each other. Why is this helpful? Because now we're going to remember that I know how to turn squares into toruses. And if I can turn a square into a torus, that means there's a way of closing these strands, so I end up with a knot. And that is exactly what I'm doing here. So if I think of these strands as living on this picture here, so let's say something like this, then these strands now become pictures on my surface, and when I draw them, you end up with a picture that looks like this. So some sort of string that's living on the surface of your torus, essentially. And this surface, this picture that's living on the surface of your torus is a knot, because it's a three-dimensional object. If you just now ignore the torus itself, it's just a knot. It's a closed piece of string. And so that's one way of viewing it. Another way of identifying this, you can see kind of in the blue pictures, in the blue strands that I've drawn, but let me draw them again, is you can imagine that I'm just going to identify these endpoints. For the sake of keeping the picture clean, I won't do it. I won't do all of them. So you can identify these guys. And then similarly, you can identify, let's pick a different color, this endpoint with this endpoint, sorry. this endpoint with this endpoint, this one with this one, this one with this one, this one with this one, and this one with this one, or something along these lines. And so the point is the number of endpoints on top and bottom and the both sides always match up, so you can always close it. And you end up with some sort of closed picture. All right, so that's the knot that you're getting. And these are the guys that we're going to call Coxeter knots. Notice they're not indexed by the curve, they're indexed by the partition. All right, because there are many, once you pick your partition, there are many curves that you can pick, but the knots that you construct up to wiggling are the same. Up to isotopy, the curve doesn't matter. Only the partition determines them. So the specific subclass of Coxeter knots that we are going to be caring about are called triangular. So these knots occur when the curve that we choose is straight. Now notice that not every partition, depending on which partition you're given, not every partition will admit a curve that is straight. So for instance, if your partition is something, what we call a hook, so something very long like this, but there's, let's say, many lattice points inside here, then if you try to draw a straight line, then because there are many lattice points inside here, then this line is not the maximal curve associated, or sorry, this partition is not the maximal partition associated with this curve, right? Because the closest partition to this curve is going to be something like a staircase. So this is an example of a partition that does not admit a straight line as its associated curve, and therefore is not triangular. So, great. So, work, there it is. Okay, and so when this happens, when your partition admits a straight line, we're going to say that the partition is triangular, and the knot is going to be a triangular Coxeter knot. So, a couple of examples. Well, first of all, this particular family of Coxeter knots that we talked about, these triangular guys, actually generalize all the previous torus knots. And this occurs precisely when the line that you're drawing, right, this line, this curve, so you have some partition, when the line that you're drawing has intercepts M and N. Now you start seeing how this connects back to dig paths, probably seeing the connection. So if I choose my curve C to be literally a straight line with intercepts M and N, then the knot that you get through the previous procedure is this MN torus knot. If your intercepts M and N are not necessarily relatively prime, right? So you have something like MD, ND, where D is the GCD of these elements, then you end up with a more complicated knot known as the DDMN+1 cable of the torus knot, which I've drawn here in this particular example. So it's something a bit more complicated. And in particular, this guy is not a torus knot. This will play a role later. So the reason this is relevant is because it's just to point out that these Coxeter knots that we're considering contain all the previous torus knots, but they contain more things than torus knots. So they are a strictly larger family than the previously known torus knots. Okay, so our goal now is to take this information, this knot theory picture, this Coxeter knot, and make it combinatorial. And the way we do this is by putting putting numbers in the partition, putting numbers in these boxes, and we're going to count some statistics, i.e. we're going to count these variables Q, T, and the associated gradings that give us the exponents. So to do this, we need a few ingredients. So our ingredient always starts with a partition. Remember that a partition is equivalent to a dig path. It's the same information. So in this particular example, let's say our partition is 3, 2. So 3, 2. And 3, 2 is the same as writing 3, 2, 0, 0. I'm just ignoring the zeros at the end. And so when I do this, erase the information that I don't need, my path is really this guy, right? And so associated to this partition, the next step is I need to pick a curve, right? So that's basically this solid line that I've drawn here is my curve. And of course, because I'm talking about triangular partitions, that means I actually want my curve to be straight, not just convex or concave or anything weird like that. And in particular, because I can pick my curve to be whatever I want, and the knot itself will be the same as long as the partition underneath it is unchanged, then that allows me to pick a curve whose slope is rational. So this is an important point. So here, let's say I chose my intercepts to be 3.2 and 5.6. So here's 3.2 and 5.6. That's a choice. You could have chosen many things. Then our next step is to take this solid line and then shift it up until you have intercepts, for example, here, that are no longer rational, but real, no longer real or rational valued, but integral. So but notice that the slope of the dotted line and the straight line are the same. So the dotted line is you take the straight line and you shift it up, keeping the slope fixed until the endpoints, the intercepts, are now integral and relatively prime. So I want the integrals, the integer or the intercepts to be relatively prime integers. So for example, 7 and 4. And for those of you in the audience who are topologists, this is essentially just embedding this Coxeter knot, which is given by the solid line, inside a larger torus knot, which is what this dotted line is encoding. All right, but when we do this, why do we need this information? Because then our next step is to take now the take this picture and put some numbers inside the boxes. So like I said, this is where the real combinatorics begins. So the way that we're going to label our boxes is via the following equation. But rather than redo the equation, let me explain how you do it in practice. So you always start by labeling this top corner by 0, right? So I want to look at the strip. So I should say, want to look at the strip of height 4. So this is height 4, but that is infinite in both directions. It's an infinite horizontal strip of height 4. And I want to start by the top corner here next to the y-axis. And I want to start by labeling that by 0. And as I move down, I want to increase each label by 7. So for example, 0 to 7, 7 plus 7 gives me 14. 14 plus 7 is 21. You increase down by 7. And that's true in general. Any of these is always going to be a plus 7 as you go down from any box to the one below it. And then to the right, as you move to the right, you want to decrease by 4. So notice that as you go here, you move by -4. So this is a -4. And so on, right? These are all -4. So this allows you to label all the boxes as long as you start by labeling this topmost corner by 0. You label all the boxes according to this algorithm. And what that does is it gives you a bijection between the integers z and every single box on that horizontal strip, because the integers are relatively prime. Once you've done this, then this allows you to do the following step, which is to look at any sub-partition, i.e. any sub-lattice path, and associate to it a subset of integers. So for instance, here, what are some subpaths of my partition 3,2, or some subpartitions? It's working. There it is. So some subpartitions, for example, I could choose this one, which is the subpartition of just this box, right? So when I do that, then the idea is that I want to assign to every such subpath, so any path that's basically below the red path here, the subset of integers I lambda consisting of all the labels to the left of it. So what are the labels to the left of this particular green boundary? Well, you get all the guys here in kind of to the left of the y-axis, and any labels that are bounded by the partition itself, in this case, 17, right? So let's do a different one. So for example, let's suppose my partition is this guy here. Then if my partition or my path is the green one, then I get all the labels. And remember that this goes on forever, right? It's a horizontal strip. So I have an infinite number of labels to the left here. So I get all the labels to the left in my set, in addition to 10, 17, and 13. So the union of all these integers that are bounded to the left by my paths, my varying paths, lambda, so it gives me a subset of integers. And you can do this for, there's a finite number of subpaths that live inside tau, inside my original partition 3, 2. And so you end up with a finite number of infinite subsets of integers indexed by these subpaths. Good. So why do I care about this? And how does our research fit into this? Like, what's the result? Well, essentially, what I did with Carmen Capral, Matt Hogenkamp, and Misha Mazen is that we defined 2 statistics, combinatorial statistics, or gradings, if you want to think of them that way, on these subsets. In particular, we were able to extract a statistic that we called area and a statistic that we called dinv, whose input is these infinite subsets. And doing this, we were able to define a new family of polynomials, which we called the triangular QT Schroeder polynomials. Here's the formula. It's some expression. The main takeaway here is that notice that we are summing over subpaths or subpartitions of this partition tau, right? So tau is this triangular guy. Lambda is like the subpaths inside it. And associated to each of these subpaths, we associated a infinite subset of integers. And then from these subset of integers, we were able to get 2 numbers, area and dinv. And these numbers are exactly the ones that are going to give us the exponents of our variables. So Q to the area, this is still very similar to what we saw before. And then T, in the previous incarnations of these Catalan polynomials, we were just seeing T to the dinv. This is a more complicated polynomial. So we have some more complicated adjustments that have to go into place. And then in addition, we also have an extra variable that's measuring some other stuff. So this is a 3-variable polynomial, but it is similar in spirit to these previous Catalan polynomials that we had studied before. Let me give you an example. I'm not going to compute it because it's a bit involved, but I'll just tell you what you get. So in this particular example that we computed in the previous page, where lambda was 3, 2, the polynomial that you get, if you were to compute all these statistics that I have not told you how to compute, I've just told you you can, you get the following polynomial. So you look at it, and it's definitely not a polynomial that is symmetric under, or at least obviously symmetric in any of the variables. And you can tell that it's something that's relatively complicated. At least certainly more complicated than QT Catalan guys. So that said, something that you do get, it actually follows from the definition, even if it's not obvious, is that when you plug in A equals 0, so you kill this parameter, what you get is actually the QT Catalan polynomial back. So you do end up with something that is symmetric in Q and T, and something that you recognize already when you just kill the A variable. So this is, again, a new polynomial that we defined that generalizes these previously already studied QT Catalan polynomial guys. Now, how does this relate to knot theory? Well, let me tell you. So first of all, like I mentioned, in general, this is true for any triangular partition. These polynomials, when you kill the A variable, right, you set the A variable equal to 0, you recover the QT Catalan polynomials. Great. It generalizes the correct thing. Second, whenever you give me any triangular partition, right, any partition where you can pick the line to be a straight line, then these polynomials that we define, these QT Schroeder polynomials, actually compute this Poincare polynomial that was coming from the knot homology side, right? So remember that I told you that given a knot, you can associate to it a chain complex. Given this chain complex, you can compute its graded dimension. This was this Poincare polynomial. And this is the guy that from a knot theory perspective, people want to compute. People either want to compute the chain complex explicitly, or they want to compute this Poincare polynomial, this graded dimension. It's very hard to do so. And we don't know in general how to do it. However, what we proved is that we actually do know how to do it for this particular family of knots called Coxeter knots coming from triangular partitions. And the way that we did it is combinatorially. And in fact, we don't just know how to do it, we give you a formula. And the formula is exactly this formula here, with the A included. This crazy formula is actually telling you something about the knots itself. It's giving you this knot invariant. Right? So the two polynomials coincide. Now, we actually get more than that. So it turns out that there's a family of much bigger conjectures underlying this whole knot theory story. One of the conjectures, due to Oblomkov, Rasmussen, and Schende, tells us that for the specific family of knots called algebraic knots, which are knots that you obtain by intersecting a three-sphere with a plane curve singularity at 0. So you intersect these two, you end up with some intersection on the three-sphere, and that intersection is a knot. And if you can get a knot in this fashion, it's called algebraic. So their conjecture tells us that when you look at the lowest A degree part, this is a mistake, this should be 1 here. This is Q equals 1, not Q equals 0. That when you specialize Q to some value, and you look at the lowest degree part of this polynomial that is now in two variables, T and A, you look at the coefficient of the lowest A degree, that lowest coefficient should coincide with some polynomial that you can get from geometry. In particular, it conjecturally coincides with the Poincare series of the compactified Jacobian associated to this singularity, to this curve that is defining your knot. Right, so this statement is something about, right, you have some sort of geometric picture, you can get a polynomial from the geometric picture, you simultaneously have some homological, more not theoretic construction, you can also get a polynomial in this way, and the conjecture states that these two values coincide, the geometric and the homological value coincide. So this is an open conjecture, it's not known in general. However, something that comes out of our result is that because for this particular family of knots, these, I gave you two examples. I said one of them was a torus knot, and I said the other one was this particular cable. So when you consider these cables, this geometric side was actually already computed. So this was computed by Gorski, Oblomkov, and Mazen very recently, a couple of years ago, maybe even last year. And what they proved is that this guy, for this particular family, this geometric side gives you the QT Catalan polynomial, right? This is the C, let's call it C lambda QT, which is exactly what our guy specializes to, right? That's the whole point. And so now, what have we done? Well, they computed the geometric side. We computed this side. So this is us. We computed this side because we computed the combinatoric resonance homology on the topological side, let's say, right? And we proved exactly that it's this polynomial that we had previously defined. And so what that means is that combining their result with our theorem, these two guys imply that this conjecture, this equality is indeed true because they proved it equals the Catalan polynomial. And we proved that indeed the lowest degree, that's exactly what this is saying, gives you the Catalan polynomial. Therefore, both sides are equal to each other, literally, right? So the conjecture is true in the special case of this family of torus knots. Oh, sorry, of cabled torus knots. And that's really exciting because this conjecture was proved as the completely unknown in anything other than for torus knots themselves, not cabled torus knots. So great. So let's see, I have 2 more minutes. Maybe let me say a couple of more things. So these polynomials that we define are not only relevant for knot theory, they also play a role in combinatorics themselves, right? They're not just things that help us learn things about knots. So there's a family of theorems called the shuffle theorems that are due to in various generalizations to the people here in this slide. And what they basically tell you is they express the action of a certain family of operators called elliptic Hall algebra operators, p tau, on symmetric functions in terms of these paths with some labels on them. The labels are different than the ones we defined. And so the idea is that if you take these operators p tau, which are elements inside this so-called elliptic Hall algebra, then when you act on the polynomial 1, you end up with some sort of symmetric function. That's what this guy is. And this symmetric function has a combinatorial formula in terms of, as you notice, q to the area, t to the div, looking pretty similar, and then some function in terms of x's. This is an infinite number of x's. And let me just shorthand this expression as d tau for the next page. So that's basically what this theorem says. And yeah, it comes in different levels of generality depending on the slope of the line. So there's some paths here, some labeled dig paths, and these dig paths depend on the slope of the line that you're defining them with respect to. Anyway, how does this fit into our story? Well, another thing that we proved is that when you look at this symmetric function that shows up in the shuffle theorem, this d tau, and you look at the components of this function that you get when you pair with what are known as Hooke Shor polynomials, or the Hooke components of this polynomial, what you get is exactly this function that we defined totally separately. Like this function a priori had nothing to do with the shuffle theorem. It was developed completely independently. It had everything to do with knot theory. And now we've come to find out that it actually also is telling us something and is related to this very celebrated theorem in algebraic combinatorics known as the shuffle theorem. So this was great. This is really cool, partly because it generalizes a previous result that was known due to Jim Haglund, known as the QT Schroeder theorem, which was restricted only to the slope being 1, but we generalized it to basically the slope being any real number that you want. And so that's really great. It's a full generalization of his theorem, but also it's the first connection that we have between knot homology or knot theory and what people call the real valued or the triangular shuffle theorem. So again, just bridging, anytime you have more connections between two areas like that you wouldn't expect to be related, you're very excited. And indeed, this is giving us not a full Schur expansion of this polynomial d tau, but it is giving us giving us some of the coefficients in some of the Schur expansions, some of the coefficients in the Schur expansion of this polynomial, which for a variety of reasons is an interesting question and is still an open problem. So we don't solve the full open problem, but we solve parts of it. And that's it. Thank you very much. I think I went 2 minutes over. If you're interested in reading about it, this is the paper that it's based on. And then the other papers underneath are kind of some of the things that we generalized and some of the papers that we used very heavily.